Hello, welcome back. So basically, we'll continue our study of the MIMO channel. So MIMO channel means multiple input, multiple output channel. It's a general term, but in the context of wireless communications, this is just the use of multiple antennas at the transmit side and the receive side. So we have our array, and again, we can place the antennas in a number of possible ways. Here we just focus on the uniform linear array, which is basically a configuration in which the antennas are placed along a line. So all the transmit antennas are placed along a line, for example, and so the direction of this line is ET, and then they are uniformly spaced, which means that the distance between two neighbors is dt. And we use nt of them, and similar thing for the receive array. And last time what we did is that we investigated what happens if a signal is emitted from the transmit array, and then the signal is scattered by some scatterer that exists with this position vector x. And again, the figure is misleading because again the assumption is that actually the two arrays are far apart and the scatterer is far from each. And then the signal, part of the scattered signal is received here by all those antennas. And we focused on the transmission by the mth antenna and reception by the nth antenna. And we discovered that basically the channel between them after approximation, so this is not like something that is exact, so the channel after approximation will be proportional to, so there is like an amplitude or complex gain, and then you have e to the I 2 pi over lambda, okay, and then if this is the nth received antenna, so we have n, and then we have ur dot er. And so ER is basically it's a unit vector that basically in the direction of the line along which the receive antennas are placed. And UR is basically this vector here. So this is the coming path. Okay, and so the coming path, it's a unit vector in the direction of the coming path. And as you can see here, you find the dot product. And because these two are unit vectors, so basically this is like cosine the angle between the array itself and the incident direction, right? So this is like cosine the angle between the array, and the array is again, the antennas are placed on a line, array, and the incident direction. Okay, and then there is another term which is minus I 2 pi over lambda. If we focus on the nth antenna, then we have m here, and so I forgot here dr. Here will be dt, the distance here on the transmit side, and then you have a similar thing, but now the angle is between the transmit array and the basically the direction to the scatterer. So this will be ut. This is a unit vector, and this is et. Okay. So this is the channel between the nth transmit antenna and the nth receive antenna. And generally speaking, if you have nt transmitters and nr receivers, total number of channels is nt nr, because like you have a channel between each antenna in the transmit array and each antenna in the receiver array. And we typically prefer like to collect those channels and put them in a matrix format, a matrix of size nr by nt. Okay, so we typically use a matrix H, so channel matrix H, and it lives in nr by nt, and element nm is the channel between the mth transmitter mth transmitter and nth receiver. Okay, so this, and this will continue with us in the remaining part of the course. Although each meter in the course will be sort of abstracted, we will not basically, we will define it as a matrix of random variables, and we will not like sort of talk about propagation and so on. Okay, so if you just have one scatterer and you want like to write down your matrix H, so you do the following: you define this vector, which is of dimension nr by 1. And this is a vector that looks like this term here, and then the index n is basically you sweep through all the values of small n, and so if the antennas are like numbered from 0 to nr minus 1, so this will go from 0, 1 up to nr minus 1. And this b vector is at t by 1, and you go here the index from 0 to nt minus 1. And the channel matrix is again proportional to the outer product. So it is A multiplied by B Hermitian, and so you get a matrix NR by T. But what is the rank of the matrix? Well, I mean, generally if you have matrices multiplied together, the rank is basically upper bounded by the smaller dimension, right? So if you have two matrices multiplied, so you have here NR, you have a 1, and then you have NT, then the rank is less than or equal to 1. Okay, it is, the rank is 0 only for all 0 matrices, so basically the rank here will be 1. Okay, those vectors are clearly not 0 vectors. In fact, the components of each vector are complex numbers living on the unit circle. Okay, so there is actually no element that is equal to 0 here. And the matrix is of rank 1, and I said last time that you may wonder about whether this is like some mathematical exercise, or in practice we do really care about the rank of the matrix. We do care about the rank of the matrix. In fact, in a system like LTE, there is something called the rank indicator. So basically, the receiver may estimate the channel, the rank of the channel matrix, and feed back this information to the transmitter so that it adjusts its transmission parameters. So we are not talking here about something that is abstract. The rank matrix is a parameter. It is something that is very important, and we will see that basically transmission in a MIMO system will depend on if you are interested in basically transmitting the most number of information bits per unit time, things will depend on the SVD, the singular value decomposition of the channel matrix, and the number of strictly positive singular values is the rank. So the rank actually will turn out to be like a practically important parameter. So that's the reason I'm talking about here. And as you can see that basically if you have just one single scatterer, no matter what NR and NT is, no matter the values of NR and NT, the rank is 1, right? Because again, you have a product, and this can be huge, this can be huge, but this is not a guarantee, right? So using many transmitters it doesn't mean that you can reliably transmit NT data streams or something like this. Things will depend on the rank of matrix H, and the rank is not just NR and NT. It depends on NR, it depends on NT, and then it depends on how many scatterers are there, and other things that we'll talk about. So if you just have one scatterer, the rank is 1. And so later, this will mean that, you can just transmit one stream of data, even if you have NT transmitters. If you have 2 paths, basically, and assuming, this is a main assumption in the course, that the wireless channel is linear, and so you apply superposition. So if you have 2 paths, okay, so you have so this is the transmitter ray, this is the receiver ray, and so there is so you go here to one scatterer and there, and then there is another scatterer, say it is here, Okay. So if you have two scatterers, you basically treat each one on its own and you sum. Okay, so each one will have its own complex gain, and then you get this weighted combination of the outer products. Okay, so now we have directions. So each scatterer now will be associated with a path with certain angles, right? So this path makes a certain angle with the transmitter ray and a certain angle with the receiver ray. The other path makes another angle and another angle on the other side. And so you have two A vectors parameterized again by the directions. Remember, the A vector itself, it depends on this dot product between this vector. So this vector depends on where the scatterer is and the array. And the other vector on the transmit side, it depends on, again, where the scatterer is. So if we are talking about scatterers in different positions, then those vectors, the U vectors, will change, and we will get two A vectors and two B vectors, and we can write down the channel matrix as this outer product, or we can write it in this nice form. So we can form a matrix A whose columns are the A vectors. So A, let's call them A. Let's actually write them explicitly. So this A1, okay. So this is the vector due to the first scatterer, and this is due to the second scatterer, okay. And then there is a B now. So this is NR by 2, and then you take your B vectors and then you can put them as rows here. So this is 2 by NT, and so here we put B Hermitian omega T 1 and B Hermitian omega T 2, okay. And then between them we put a diagonal matrix, and this diagonal matrix basically it indicates the complex gain of each path, and so this is alpha 1 and alpha 2. Now, so if you look here, now if in the presence of two scatterers, basically you get to those dimensions. So now you have a hope that your rank is 2. Okay, so again, NR can be huge, NT can be huge, but if the channel matrix is the product of these three matrices, then the rank is basically determined by the smallest size, which is 2, and it can actually be less than this smallest size. Okay, so here the rank is 1 or 2. Okay, and I will talk about this. So it's not just that, you know, it may be 2 or not. So it turns out that it's not that you need two scatterers to get a rank of 2. You need also another condition that I will talk about shortly. Okay, and here let's scroll to the general case. So the general case, if you have L scatterers, okay, then your channel matrix is basically the outer product, a weighted sum of the outer products of A vectors and the B vectors, okay, which can be written as the product of three matrices, a matrix whose columns are the A vectors. Again, the A vectors are parameterized by the directions between the incident path and the array. And then here we have a matrix whose rows are the basically the Hermitian. So we need a Hermitian here. Rows are basically the Hermitian of the B vectors, and those are parameterized by the angles between the transmit arrays, the line along which the transmit antennas are placed, and basically unit vectors pointing to the scatterers. And in between you have a diagonal matrix with those both gains. And so the general thing is that matrix H can be written as a matrix that is NR by L, okay, this one, and the matrix that is L by L, and the matrix that is L by NT. So typically we want a rich scattering environment. So we want L to be high. If L is high, then basically the rank will depend on NR and NT, and also about something else, you know, that I'm about to talk, Okay, so now generally the rank of H will be upper bounded by the minimum of those guys, NR L and NT. So you can see the problem. If you don't have enough scatterers, if L is small, then the rank will be determined by L. It will be upper bounded by, the few scatterers, the number of, of the few scatterers that exist between the transmit and receiver rays. If you are in a rich scattering environment, L will be large, and now, it becomes a business of what is the minimum of NR and NT, and also something else I need to talk about. Okay, so this is very important. Again, it's not just, it's not a linear algebra problem in which like you have a matrix written as 3 matrices, and you just wonder for out of mathematical curiosity what is the rank. Okay, this is important. The number of data streams that can be reliably decoded basically is the rank of this matrix H. So what other problem can arise? So here I said that the rank is less than or equal to the minimum of these 3 quantities. Can it be strictly smaller than those? In other words, like in the 2 by 2 case, can the rank actually be 1, still be 1? So the rank is 2 or 1, but can it be 1? And what is basically the situation in which it is 1? So we have 2 scatterers, but basically it's the performance as if we just have 1 scatterer. Okay, so what will make this rank equal to 1? So let's go back and focus on the 2 by 2 case. And so again, matrix matrix H is A, and then you have this matrix, diagonal matrix, and then you have B1 Hermitian, B2 Hermitian, right? So what is the rank? What is the rank of H? Well, again, it depends on the rank of each of these matrices. Let's focus on A. So A is NR by 2. Can A have a rank of 1? So it will have a rank of 1 if its columns, so it has 2 columns, but perhaps the columns are very close to being linearly dependent. Okay, so that's the case in which A will have rank deficiency and its rank will be 1, and if the rank of A drops to 1, then the rank of H will drop to 1. Okay, so let's just focus on matrix A. The rank of A, so we know that the rank of A is the same as the rank of A Hermitian A. And so we will study A Hermitian A. So this is A Hermitian, and this is A. And the product of A Hermitian A is given by basically a 2 by 2 matrix. So this is 2 by NR, and this is NR by 2. And so the product is a 2 by 2 matrix, which is given as such. Okay, so why is this the case? A itself, it looks like this. So it have 2 columns. And so it have like E to the I 2 pi over lambda 0. And then we have dr. And then we have basically omega r1. Okay, which is omega r superscript 1, which is basically, it is the dot product of ER. So that's the direction of the receive array, and then UR1, and so UR1 is the incident direction of the first path from the first scatter. Okay, and so this one here will be e to the I 2 pi over lambda 1, then dr omega r2 omega r1 also. So basically here you increase the index. So basically this is a representative of the antenna. The second column will be exactly the same, but you will have, okay, so let me erase this one. It will be exactly the same, but you will have the parameters omega r2. Okay, so this is e to the I 2 pi over lambda 1 dr omega r2 and so on. So what we do is that we multiply this matrix from the left by its Hermitian. Okay, so this will be, those guys will have a minus sign, okay, dr omega r1, and then e to the minus I 2 pi over lambda, then 1 dr, then omega r1, and so on. So you can see that if you multiply this first row by this first column, what do you get? You get, so this multiplied by this, each element is the reciprocal of the other, so the product is 1, and then you sum them, and so you get NR. Okay, so element 1, 1 in this 2 matrix is NR, and similarly, element 2, 2 is basically NR. Okay, again, because you are multiplying this vector. This is a very specific vector, elements again living on the unit circle in the complex plane. So basically the conjugate multiplied by the element will give you 1, and you have NR1s. And then you have two cross terms that are complex conjugates of one another, and the cross terms again they come from what if you take this guy and multiply it by this guy here. Okay, so here I put it as gamma conjugate, and gamma itself will be 1 over NR. This 1 over NR is because like I assume that rather than writing those two terms, one term and two term as NR, I will take NR as a common factor, and so whatever I have here, I just need to put 1 over NR, and then you have an inner product, so you have a summation, and this summation will basically look like this. Okay, so if you take this guy with this guy, or the second, specifically the second row with the first column, you will get e to the I2 pi dr over lambda, then L, and L basically goes from 0 to nr minus 1, and then we have the difference between these two quantities, omega 1 and omega 2. Okay, so this is our this is A Hermitian A. Now the rank of A is the same as the rank of this matrix. Okay, so A Hermitian A is a Hermitian positive semi-definite matrix, and actually its rank is equal to the number of positive eigenvalues. And so what are the eigenvalues of A Hermitian A? Okay, so basically it's a rank, it's a matrix, the trace is 2nr, and the determinant, which is the product of the two eigenvalues, is nr by nr minus nr squared, and then you have magnitude gamma squared. And so basically each eigenvalue, so we have two eigenvalues, one of them is nr1 plus magnitude of gamma, and the other is nr1 minus magnitude of gamma. So you may look here and say, well, and what is gamma? Gamma is this quantity here. Let's look about gamma. What is the magnitude of gamma? What is the magnitude of gamma? It's the magnitude of this sum, okay? And if you apply the triangle inequality, then this will be 1 over nr, summation L from 0 to nr minus 1, and then the magnitude of the exponential. And each guy here has a magnitude of 1, and so if you sum nr of them, you get nr divided by nr, that's 1. So the magnitude of gamma is upper bounded by 1. So this is like sort of an eigenvalue. Its least possible value is nr, right? When magnitude gamma, if it's 0, then this is nr. Now, if the magnitude of gamma is somewhere between 0 and 1, then this is actually greater than nr. So this is like sort of not a problematic eigenvalue. We are sure that this eigenvalue is positive. What about the second eigenvalue? The second eigenvalue basically can reach 0. It can reach 0. So basically, in the extreme case in which the magnitude of gamma becomes 1, then this second eigenvalue will be equal to 0. And in that case, we have one positive eigenvalue and one zero eigenvalue. And so the rank will be equal to 1. And if the rank of matrix A Hermitian A is 1, then the rank of A is 1, and then the rank of H will be 1. Okay, so we get rank deficiency, mathematically speaking, if the magnitude of gamma is 1. Okay, so this is if we talk mathematically, okay? But from a practical point of view, the matrix is rank deficient, so its rank is 1 and not 2, if magnitude of gamma is close to 1. We do not really need it to be exactly 1. If it's close to 1, then the so-called numerical rank. So this is the rank that is sort of relevant to practice. Because in practice you will do things. You will carry out computations on a digital signal processor. Okay, and so in that case, you don't care about the mathematical rank, you care about the numerical rank. Okay, so that's the reason. I'm sure that at least some of you have encountered this. Sometimes you solve a linear system of equations on MATLAB, and then you get a warning that the system is ill-conditioned, or some matrix is ill-conditioned. So that's the situation, that basically you have a matrix, for example, whose determinant is very close to 0, or it's very close to being rank deficient. And numerically, typically the decision is made based on the singular values of the matrix. So basically, the singular values of a matrix are computed, and if you have a matrix n by n, but then one or more of its singular values is tiny, is much smaller than the maximum singular value, then your matrix, from a practical point of view, from a numerical point of view, is rank deficient. Okay, so basically, you get magnitude gamma equals 1, so that's the mathematical case, if, for example, these two guys are the same, which means that if the two scatterers are sort of co-located, they are in the same position. If they are in the same position, then you will be in a situation which basically this difference is zero, and all terms in the summation will be 1, and the gamma will be equal to 1. Okay, but in practice, if these two guys, we need these two guys to be close to 0. If this difference is close to 0, then you are in trouble, because if these two guys are close to 0, magnitude gamma, it will not be 1, but it will be very close to 1, such that for all practical purposes, the matrix has a rank of 1 and not 2. Okay, so basically this is the story here. We are in trouble. We have rank deficiency if basically the difference between these two guys is close to 0. So of course, if I say close to 0, it's like, how close is close? What do you mean close to 0? So let's see. The problem, if you have this angle, right? If you have e to the I 2 pi multiplied by something, so it's dr over lambda omega r1 minus omega r2 multiplied by the index L. Okay, so maximum index L is nr minus 1. Say it's nr. Okay, so it's like the guy here is the maximum value is dr over lambda omega 1 minus omega 2 nr. Okay, and so being close to 0 means that this guy is much smaller than 1. Okay, so this is basically the way people, like, even in practice, think about it, that you have rank deficiency if this difference is much smaller than dr over lambda nr. Lambda, I did it. So lambda, so lambda will go here to be in the numerator, lambda over nr dr. Okay, so lambda, which is the wavelength, and nr dr basically is sort of the linear extent of the array. So sort of the linear extent of the array. In space. Okay, so basically this is the condition. If this difference of omegas is much smaller than this quantity, so when we say it's a small relative close to 0, it means it's a small relative to what? Okay, so basically small to this particular quantity, lambda over nr dr. Then the rank is, for all practical purposes, is rank deficient. Okay. Now, physically, what is those omegas, and what does it mean that the difference between them are small? So basically, omegas are cosine angles, right? So basically, it means something like this. So you have, this is the receive, so this is ER, and then suppose that this is one path. Okay, so here it's come from scatterer 1, and this is basically, so this is direction UR1. And suppose that you are to something very close. Okay, so if this guy is very close, okay, then you are in this situation. So those are directions, right? And so it means that let's put it like in simple English. If the two scatterers if the two scatterers result in incident waves on the receiver ray that are very close to one another in space, okay, so they come almost from the same direction, okay, then it's as if we have just one scatterer. It's as if we just have one scatterer, and the rank of matrix A will drop to 1. The same story can be said about matrix B, but it can be told, basically based on the transmit array. Okay, so here I focused on matrix A, but remember that H is A times, this diagonal matrix of complex gains times B. So you are also in trouble if you have basically the directions. Okay, so suppose that you have the transmit array, and you are in trouble if you have a scatterer 1 here, a scatterer 2 there, and then the directions are very, very close. Okay, in that case again matrix B will be practically rank deficient, and if the rank of B is 1, that's it for matrix H. A product of matrices is under the mercy of the smallest dimension, okay, or the smallest rank. Okay, so you get a rank deficiency in any item in the product, and then basically the product itself will have rank deficiency. Okay, so basically this is the story. If the angular separation is very small, and again very small based on the expression on the receive side, we take it smaller than this quantity. On the transmit side, we take it much less than this quantity. Then we have rank deficiency. Okay, so here is a comment again that I will put in red here, because rank is 2. Rank is 2 if the magnitude of gamma is less than 1, but numerical rank is unity. Okay, so you need here basically to differentiate between the mathematical, pure theoretical stuff and the practical stuff. So for example, those of you taking with me the other course, you will in homework 2 you will prove that full rank matrices are dense. Okay, full rank matrices are dense. Which means that if you have basically any matrix, you can always find even a singular matrix, you can always find a full rank matrix that is close to that matrix, to that arbitrary matrix. Give me any arbitrary matrix, I can give you a full rank matrix that is very, very close to it using some matrix null. Okay, so here the talk is about mathematical rank. Okay, we don't, if the minimum singular value of a matrix is like 10 to the minus 15, well, from a mathematical point of view, well, this is strictly positive, and we have full rank. But practically speaking, no. Okay, so you need to basically put this difference in mind, because sometimes you have two hats. Sometimes you wear the hat of doing like theory, and sometimes you need to think like sort of practically. Okay, so these are two situations. Like, so here is a situation which, like, the transmit array, all the scatterers. So basically, here the scatterers are clustered around the far receiver, right? And so what is the problem? So basically for the receiver ray, so here we have scatterers around it, okay, from many directions. And so you may say, hey, we have like, the coming waves, they come from, directions that are significantly different from one another. But in this scenario, we have a problem. The problem is here. Basically because all the scatterers are very far from the transmit array, and they are clustered around the receiver. So if this is the transmit array, so basically the vectors, you transmit 1, and you transmit 2, and you transmit 3, those vectors are close to one another. And so, basically here we will have basically a matrix B will be rank deficient in the practical sense. if B is rank deficient, then H is rank deficient. Here is like a different scenario in which basically the scatterers, so here, the scatterers cluster around the transmitter, and this is good. But look here from the point of view of the receiver. So this is the receiver ray, okay? Now, those guys are close to one another. Okay, you are 2 and so on. So here what we have is matrix A will be rank deficient in a practical sense. Okay, so to make matrix H with the highest rank possible, and so the highest rank, if you have enough scatterers, in the environment, the highest possible rank of matrix H is the minimum of NR and NT. So how can we be sure that we can obtain this rank? We can obtain this rank, again, so you need so many scatterers, but you need something else. You need something else. It's not just that you need scatterers, because the scatterers, their physical position may lead to rank deficiency. Okay, so we need, so what are our needs? Okay, so rank H to be min NR and T. So what is needed? L, so number of scatterers is large. Definitely it needs to exceed those two guys. Okay, what else? Is this enough? No, we need large, let me write it here in red, angular spread on both sides, on both the transmit and receive sides. Which means that, you receive, with directions, along directions that are sort of far from one another. I mean, if you basically get from a narrow angle, if you receive your stuff from a narrow angle, or if the signal received comes from basically a narrow angle here from the transmit side, then you will face a problem with either matrix A or matrix B, and in both cases you will have trouble with matrix H. So we need large angular spread. Okay, so these are very important in practice. Like if you are a working wireless engineer, you need to know these things. So moral of the story is, I mean, we will come back to MIMO later in the course, but moral of the story, just the deployment of multiple antennas is not enough in and of itself to give you enhancement in performance. If our goal is actually to increase the rate, and this is the goal of like every next generation of a wireless standard, then you need to make sure that actually the environment and the antennas deployed in the environment will actually give you a matrix H without rank deficiency. Okay, so we need a rich scattering environment, and the scatterers must be sort of everywhere around the transmitter and around the receiver. You need to receive your signal from a large angle. Okay, and so more about this in homework 3. So before, like in the course, we go back to MIMO. More about this, like you will solve a nice problem actually that gives you again more intuition about like basically MIMO channels. Okay. Now, I mean, again, you can say a lot about wireless channel modeling, but I think it's now, for the purposes of our course, it's now like the time to start performance analysis. Okay, so any questions? Okay, so let's go. SISO now. So we are back to a case in which we have a single transmit antenna, a single receive antenna. Okay, again, we need like to learn a couple of tricks based on the system with just single antennas, single users, and so on. And then later we will come back to MIMO systems. Okay. So flat feeding, so this is like the thing that we will focus about initially till we study OFDM, flat feeding. So flat feeding, remember, flat feeding means what? Flat feeding means a number of things, okay? Means that bandwidth of the signal is much smaller than the coherence bandwidth of the channel. Okay, so basically the spectral components of the signal are close to one another relative to the coherence bandwidth of the channel. So in the frequency domain, I mean, the spectral components are encountering almost the same channel, okay? So the channel can just be represented by complex number. But you can also understand things from the time domain and say that basically flat feeding or frequency non-selective feeding or narrowband means that the delay spread is much smaller than the symbol duration. Okay, and this actually is like sort of more intuitive than this one. This is like direct in the time domain, and like 2 lectures ago, I basically gave you this in which like we transmit some pulses, and then if the delay spread is very small, then you discover that if you take a sample in the receiver, the sample will depend on just one transmitted symbol. And so again, we are here saying that your received signal will not be like a linear combination of some symbols or an integral or anything. Your received signal is just one symbol multiplied by a complex number, the complex number denoting basically the effect of the channel in terms of magnitude and phase. Okay, so our general model is this. Okay, so this is actually the received signal. Of course, this is not a general, it's a general model for us, but actually, if so many assumptions actually to even reach this stage, okay, FD Doubler and the tau, and this guy here is V over lambda cosine theta of tau, okay. So under flat feeding, you can just write down a symbol, okay, and then an integral, which is G of t, and this G of t here will be represented as H. Okay, so your received signal model, this is a model that is used in many papers. It's not the only model. There are other models that are not normalized. This is called the normalized model, and I will stick to it in the lectures. But in the exercises, I mean, you will deal with it and deal with other models. This model is very nice, and we'll see how things are defined. So this is the received signal. The received signal is Y, and it is 2 components, as in communications. So basically, a signal component and additive white Gaussian noise. So the additive white Gaussian noise, it will have normalized variance. So we'll take the additive white Gaussian noise to be basically circularly symmetric Gaussian. Okay, circularly symmetric complex valued Gaussian. Zero mean and unit variance. Okay, so it's a standard. So that's the normalization. We don't say that sigma squared or something. It's just 1. And the noise is independent of the transmitted symbol and of the channel. X is the transmitted symbol. It's a zero mean. It's taken from one of the constellations. So typically Quam constellation. And the variance of X is taken to be equal to 1. H is it's a random variable that represents the channel. It's a random variable that represents the channel. And basically, this random variable is independent of the transmitted symbol and independent of the Gaussian noise. So the Gaussian noise basically is a signal that is basically or that contaminate your useful signal due to the receiver electronics. Like whenever you receive a signal via an antenna and you amplify this signal, the amplifier is built using electronic devices, and those devices will, they are noisy. it's a random variable because we don't know which symbol. Okay, so x is from the point of view of the receiver. Basically, when you get the received signal y, basically x can be any of the transmitted symbols, and typically we consider all symbols to be equiprobable. Okay, and the question basically, or the challenge for the receiver is to detect x, is to tell which symbol, right? So x is treated as something that can be, if you use 16 QAM, it can be one of 16 possibilities, and the challenge is to tell which one. Okay, that's exactly the detection or hypothesis testing problem. Okay, now H itself will also be considered to be CN01. Okay, so H also is CN01. I will talk shortly about what is this guy living here. This guy is, according to what I said, you think that there should be some constant here. Otherwise, like the signal to noise ratio is 1, right? Without this term here, I am basically normalizing everything to have a unit variance. H is unit variance, epsilon is unit variance, which is the noise, x is unit variance. Well, I mean, we need a factor to tell us, that the signal component is, let's say, 20 times higher in power than the noise, and so on. Okay, so this role will be played by this this quantity. But before like I talk about this particular factor, where is time? So I spent the previous part of the course talking about the wireless channel, the multi-path wireless channel being not just a random variable. It's not just a random variable. It is a random process. Remember, it's a g of t. Okay, again, you fix t. When you fix t, it becomes a random variable. But generally, it is something that is continuously changing over time. Okay, so it is g of t, and then now I am writing it without t. Okay, so I am writing it without t. So what is the story now? I mean, what is this? So there is an assumption. To be able to write down this, there is an assumption. Okay, and this assumption will always be with us in this course, and actually I think in the perhaps in the overwhelming majority of papers, is that the channel changes over time. That is true, but it does not change like in very in a very fast way, unless you are moving in a very fast, very quickly. If V is huge, then the channel will basically will change very rapidly. But in all cases, even if the channel is changing more rapidly with time, typically the symbol duration is much smaller than the coherence time of the channel. Okay, so this is a very important assumption. The symbol duration is much smaller than the coherence time of the channel. Remember the concept of coherence time. Coherence time means if you study the channel at T1, if you study the channel at T2, and the separation between T1 and T2 is much smaller than the coherence time of the channel, you will find that the channel at T1 and the channel at T2, the channels at T1 and T2 will be highly correlated. In fact, we can take them to be the same channel. And vice versa. If you study the channel at T1 and T2 and the difference in time is much greater than the coherence time of the channel, then most likely, the channel at T2 is some uncorrelated or even independent of the channel at T1. So when I say that the symbol duration, okay, is much smaller than the coherence time of the channel, this means that the channel is almost fixed over a symbol. In fact, for a communication system to work, we typically want the channel to be fixed over a bunch of symbols, over a bucket of symbols. Okay, so so again, this is very important that we assume the channel. So the channel is varying over time. It's continuously changing over time. That's true. I mean, otherwise, all the previous stuff is like meaningless. The channel is a random process and it changes over time, but we assume the channel is almost fixed during the transmission of a number of symbols. A number of symbols. A very important assumption. And so under this assumption, you can just think of the channel. So it's as if it's a random process, and you study this random process at a certain instant of time. And so it's like you are extracting a random variable from the random process. Okay, so that's the idea here. Okay, it's the idea is that you are treating the channel in this received signal model as a random variable, again because the symbols, the transmitted symbols, are transmit. We design the system so that the symbol duration is much smaller than the coherence time of the channel. So the channel is almost constant over the transmission of not just one symbol, but a bucket, a certain bucket of symbols. And hence we can just treat the channel as a complex number. So it becomes like, specifically it's a complex random variable, and we can basically drop the dependence on t. We will take it into account in different ways, as we will see later in this course. Okay, so again, the channel is time varying, and this will have an impact, and we will actually study this later. Okay, so that's basically our model. You need to basically absorb this model and like understand it very well. So there is the received signal model. So this is the received signal at the receiver. It's the baseband received signal, of course. It's the baseband model. So this is baseband received signal after down conversion, and this is the transmitted symbol. It's one of the symbols in a constellation. Typically, those are equiprobable from the point of view of the system. And there is this channel gain. It's a flat fading model. I do not need like to have like summation or integral or anything. Basically, there is a channel here which is just a random variable under our assumptions. There is additive noise, okay, additive Gaussian noise, and we take CN01 for this and for H, and X is from a constellation. We take everyone to have unit variance, to be zero mean and have a variance of unity. We are still left with this parameter here. Okay, so when you have a fading channel, you have two types of signal to noise ratio. Okay, so compare what I am about to say with like a previous course on digital communications, like 242. Here we basically have two definitions for the signal to noise ratio. So the first definition is the instantaneous signal to noise ratio. Instantaneous signal to noise ratio. And in the instantaneous signal to noise ratio, we do not deal with H as a random variable. We deal with it as just a constant that is there. We deal with X as a random variable. We deal with epsilon as a random variable, but not H. And so the signal to noise ratio, it means that you go to the signal component, take its magnitude squared, and to the noise component, take its magnitude squared, and you compute the ratio. So here it is. So you have, again, let me copy from above. We have SNR HX plus epsilon. So you go to the signal component, take the magnitude squared, and then you go to the noise component and take the magnitude squared, and then you apply expectation. So you apply expectation to what? To what random variables? We have three random variables, H, X, and epsilon. So what we do for the instantaneous signal to noise ratio, we take expectation H and X, epsilon and X. in the whole expression. So in the numerator it will be x. Okay, so just put it like this, x. And in the denominator we put it with respect to epsilon. Okay, so you put the average noise power, the average signal power, averaged over the constellation. So here we talk about the average of the constellation, which is taken to be. What about h? No, you treat it, you given h. So this is the secret here, given h. And hence your result will be a function of h. So you get so this expectation is equal to 1 under our assumptions. This is equal to 1 under our assumptions. So this is the instantaneous. So it's this mysterious constant multiplied by the magnitude of h squared. So this is the instantaneous signal to noise ratio, or you can say that it is the signal to noise ratio given the channel, treating the channel as if it's just some complex constant that is living there, basically affecting the amplitude of the received signal. What about the average SNR? So the average SNR, you basically take this a step further, and you also average over the channel. Okay, so average SNR. So here we use the average of the symbols, noise, and channel. Okay, so you take the expectation of this thing with respect to the channel, and since we take the channel to be Cn01, so the variance is 1, and then you get this parameter. So this parameter I will put in the received signal model. It has a meaning. Okay, so I will write down something like y square root SNR hx plus epsilon. This number is the average signal to noise ratio, averaged over empty. Okay, so that's this number here. And so if you want to select the signal to noise ratio, you want to study your system with a certain average signal to noise ratio, you just play in with this number. You put it 10, you put it 15, you put it 20, okay, you put it 7, whatever. Okay, so this will be the number. Okay, so so the model is normalized, like so the benefit here is like you put you put the signal to noise ratio explicitly as this factor, and then you deal with normalized random variables, which is in many times is like convenient. Okay, so rather than saying epsilon, it has a variance of sigma squared, x, it has a variance px, h, it has a variance p sub h. Okay, so rather than doing this, you just set everyone to have unit variance and just put a constant here in this form. And again, this is this constant, it has a meaning. So if you write y square root 10 hx plus epsilon, so if you write it like this, this means that the average SNR is 10. NR is equal to 10. Okay. And again, the idea is that you need to think about so in a previous course, perhaps you have like this signal to noise ratio, like signal power over noise power. Now we have a channel. So now we have a new player, which is the channel. And so, well, you can treat the channel as constant, and in that case, you get this concept of an instantaneous signal to noise ratio, or the signal to noise ratio given the channel. Or you say, okay, I will also take the average, over the channel. So you take the expectation of magnitude h squared, and this, will give you the average signal to noise ratio. Okay. The channel in this course, again, I will take it to be this model here. There are so many models for, which means so many distributions for fading channels. This will be my focus. And you can show that basically if H is circularly symmetric, complex valued standard Gaussian with zero mean and unit variance, then the magnitude of H squared is exponential with parameter 1. And the magnitude of H itself will be Rayleigh distributed. So Rayleigh is a distribution. In the literature, we call the channels based on the distribution of the magnitude. No, it's not the amplitude of in practice. No, in practice everything like has a number. So like basically the power of the noise is like 10 to the minus something watts. Okay, there is, got what I mean. So basically everything will have a certain value. Here we abstract things. We just why do we, I mean this abstraction, by the way, is not even an approximation, because what you really care about in terms of performance is the ratio, is the ratio of signal power to noise power. Okay, so mathematically speaking, you can write it. So rather than like writing things like with actual powers, why not normalize? For example, just assume that the noise power is 1 watt. There is no noise power in receivers that is 1 watt. Assume it is 1, and then adjust everything based on that, because what matters is the ratio. Okay. Okay, so this is again, here we are not, to make life simple, we are not tracking the powers, we are normalizing them, and we are writing basically this model in which the signal to noise ratio is captured by this number that you will see written in front of hx. As I said, basically the channels are named based on the distribution of the channel magnitude, not magnitude squared. Okay, so our channel model will be called the Rayleigh channel model, and I am sure that you read this before in many places. So we are talking about the Rayleigh channel or Rayleigh fading channel, and it's called Rayleigh fading channel, but we will rarely use the Rayleigh PDF. Because typically in this course we will either use the PDF of H itself, which is complex Gaussian, or the PDF of magnitude H squared, which is exponential 1. Okay, but the channel is called Rayleigh again because the name is related to the magnitude of H. So this is our standard model in the course. So if I do not say anything, then that's the default basically channel model. Okay. In a previous course, you learned how to compute the probability of error. How can we do this right now? Now with this H. Okay. So here is the procedure. We condition on H. We first treat H as if it's non-random, as if it's deterministic. It's a constant. Okay. And we do our computation of the probability of error, or the average probability of error, conditioned on H. And then later, we say, well, I mean, so basically H, if I transmit a symbol right now, H will take a certain value. If I wait for, some time, then H will assume a new value, and, my performance will change. So what is the average performance? So we will average over H. Okay, so in performance analysis for multipath fading channels, we initially treat H. Okay, and this will actually, even in MIMO systems in which this small h will be the capital big H matrix, we treat the channel or channels as fixed, as if they are non-random. And then we take the randomness into account later in the analysis. But this procedure actually, this is the math. But here in this particular case, it has also a meaning in practice. If we solve the detection problem to know X given H, it means that H is some known number. Okay, so you know H, so it's known. So what does this mean, practically speaking? This means that the receiver estimates H before detecting X. Okay, so yeah.
The same as with what we did in sending the pilot and estimate the channel effect.
Yeah, yes, exactly. So that's that, and we'll we will analyze the system with pilots in the next lecture. Exactly. I mean, the idea is that in wireless channels, okay, you will need to know H first. Okay, so you estimate H. And when you solve the detection problem, you solve it knowing H. Of course, you can never know H perfectly, because to know H, you don't really know it. You estimate it, and any estimate is noisy. Okay? So initially, I will study the system given perfect knowledge of H. And in many papers, this is what is done, that you assume that you have perfect estimates of the channel gain at the receiver. And then, in the coming lecture, I will basically give you a flavor of how things are analyzed if we estimate H. And to estimate H, as you heard the question, to estimate H, you will need to transmit something called the pilot symbols or the reference signals. Okay? But for now, we will assume that the estimate is perfect. Suppose that X is binary PSK. If it's binary PSK, then we are basically solving a binary hypothesis testing problem. We are asking ourselves the question, X is +1 or X is -1. We want to minimize the average probability of error, so we'll go for the MAB rule. But since these two guys are equiprobable, then the MAB rule becomes the ML rule. And because our noise is Gaussian, then actually we are talking about the minimum Euclidean distance rule. Okay, so we start with the MAB rule, and typically, I will rarely do this again. I will simply start from the likelihoods later, but like if you want to do things in very slow motion, minimizing the average probability of error, it means MAB rule. Then you apply Bayes. Then if the priors are the same, here each prior probability is equal to 1/2, then it becomes a comparison of the likelihood functions. So MAB becomes maximum likelihood. You see which likelihood function is greater. And the likelihood function here is Gaussian. It's Gaussian because the noise is Gaussian. Note that we are doing everything here conditioned on H. So basically, this is the distribution of Y. So Y given H is complex normal. Its mean value is SNR HX. And its variance, so given this quantity, its variance is 1. And this is the complex valued, Gaussian. So, this is the distribution of the circularly symmetric complex valued Gaussian. Okay, it looks a bit different from the real valued Gaussian. So you need to use this. And you start basically simplifying, as I said in the previous lecture. So you eliminate those, you take the logarithm, which is a monotonic function, and then you multiply by -1, reversing those inequalities. And so now you have your rule is minimum Euclidean distance. Minimum Euclidean distance. Okay? Because if you see this detection rule, it's you take your received signal and you measure its distance. So you measure basically the distance between Y and square root SNRH plus 1. And you measure the distance to the other alternative, which is square root SNRH multiplied by -1. So this is the signal term when X is plus 1. This is the signal term when X is -1. So you measure the distances and you compare them. and so that's our receiver will be a minimum Euclidean distance receiver. But we do not stop here. We simplify. This is the magnitude squared of a complex quantity. We write it as the product of the complex quantity by its complex conjugate. And we will discover that there are terms that can be eliminated. You multiply y by y conjugate, it gives you magnitude y squared, but also you get magnitude y squared on the other side. So these guys will go away, and same for S and R magnitude h squared. And so the remaining terms can be gathered as such. And note that when in the complex case, when you multiply, the cross terms will be a term and its complex conjugate. Not like what I did in the previous lecture, in which the cross terms are equal and you can combine them and put 2. But now they are one, a term and its complex conjugate. Okay? So you need to simplify. I don't need to repeat myself. As I said, I emphasized in the previous lecture, you start with a certain detection rule, and then you need to put it in the most simple form. And the most simple form in our case will be this form here, which tells you want to make a decision regarding whether +1 or -1 was transmitted. Here is the way to go. You need first to know h. Okay, so you go and estimate it, and suppose that we have this estimate and that it's even perfect. Then you need to compute this decision statistic, h conjugate times y plus h times y conjugate, and compare this with 0. If this is greater than 0, we say that the symbol is +1. Otherwise, we say that it is -1. And alternatively, basically, this is a complex quantity by its conjugate. So we can basically take the received signal y multiplied by the conjugate of h, and see, you see why we need to know h, right? Because how can you even compute this quantity without knowing h? So we need to estimate h and know it. Okay, and then you take h conjugate multiplied by y, you take the real part, and then you compare with 0. If you get something greater than 0, then you say that +1 was transmitted. Otherwise, you say that -1 was transmitted. But of course, you can make an error. So basically, this decision statistic may exceed 0, and you say +1, but actually it may be the case that x is -1 and vice versa. Right, so the noise, this decision is not this decision rule is not guaranteed to make the probability of error 0. This decision rule is guaranteed to yield the minimum average probability of error. Okay, but there is some positive probability of error. Okay, so what is the probability of error? So that was the homework problem. So this is the case. This is the general formula. I am providing it here because it's very important. So it is the Q function, and then the square root. So this is the general case if our observations are even vector observations, and basically we have under h0 we have a mean different from under h1. Then this is the formula. So keep it. It's very important. Here in many parts of the course we will deal with a special case. So the special case is when the correlation matrix of the noise is basically diagonal multiplied by some positive parameter sigma squared. So if R is equal to sigma squared I n by n, then R inverse becomes 1 over sigma squared identity. And so in that case the probability of error becomes the Q function, and the square root, you get a sigma squared in the denominator because of this inverse. You get the reciprocal of sigma squared, and then this guy mu1 minus mu0 Hermitian multiplied by identity multiplied by mu1 minus mu0. This will give you the L2 norm squared of mu1 minus mu0, and so we'll call this a distance, right? Because this is like sort of a Euclidean distance. Euclidean distance between the noiseless alternatives. in our case here in the lecture, actually even sigma squared, because sigma squared is the variance of the noise, and we are normalizing our stuff. So basically, this will be 1, and this is our formula. So BE is Q square root D squared over 2. Very important, okay, to keep those, because these are basically the formulas that you will use in the course. So it turns out, like, once or let's put it this way, your focus now to compute the probability of error will be the distance, right? It's sort of Euclidean distance. That's the advantage of Gaussian noise. It makes the computation of a probability of errors like you compute a distance. And so here, what are our two noiseless alternatives? So basically, we have one alternative is square root SNR times H times plus 1. So that's when X is plus 1. And then the other possibility is minus square root SNR H times. So it's basically, I can write it as square root SNR H times minus 1. This is when X is minus 1. And basically the distance will be, you take, basically, what is the distance between these two guys? So it is the magnitude of square root SNR H minus square root SNR H, and square root SNR is just a real valued positive quantity. So you get a 2 square root SNR multiplied by the magnitude of H. So you take this D here and insert it there, and this will be, in our case, it's the average probability of error, but here it's like sort of average. If we, here we are treating the noise as our random variable, so we get this Q function because the noise is Gaussian. But in our case, it's not just, we have an extra random variable which is H. Okay, so here what we get is the probability of error conditioned on H. Okay, so again, let me summarize. When you solve that for the average probability of error in a system with fading, your first step resembles, a standard AWG channel. What you do is that you know that there is a channel. It is a random process, but it's a random process that is like sort of treated over a very short period of time, so we can consider it to be just a random variable. But then you also fix this random variable. You condition on H. You treat H as if it's fixed. And then you solve your detection problem in Gaussian noise, treating H as a constant. And and so basically your results at this stage are expressible in terms of the Q function. Because once H is fixed, that's it, right? It becomes just a parameter that is multiplied by X, and now your random variable, that is basically the noise contaminating the signal will be epsilon. And because it's Gaussian, we express things in terms of the Q function. Okay, but then we need to consider that H is indeed a random variable. Okay, so this is, so basically on the next page, I will just take this D and insert it in the Q function. Okay, so this is the distance. This is the distance between basically the two cases, the two alternatives, the two hypotheses, right? And what we get is not the average probability of error. We are not done yet. What we get is the conditional one. Okay, so what we get here will be the conditional probability of error given H, and you just plug in, you take the distance and you put it here, and so this is basically the probability of error given H. Okay, any question? We are not done yet, right? So this gives you the performance of the system like what you studied in a previous course, for a given value of the channel gain. But I mean, the channel gain, basically it changes over time. right? Because there is mobility, you know, so basically sometimes this magnitude h squared is high, sometimes it's low, and so on. And so we average. So basically I took h squared here, called it g, and then the average probability of error, okay, will be this quantity, this q function, averaged over g. Okay, so basically we take the q function multiplied by the PDF of g, and then we integrate. Okay, so basically you condition on h. When you condition on h, you get the benefit of having a problem, standard problem in additive wide Gaussian noise, with, you know, with a channel with a constant or fixed amplitude. You get your result in terms of a q function, and then you average, you know, so basically you use the distribution, you know, for the channel gain, so that you get the average probability of error. Okay, so in our case here, it turns out that this averaging can be done. We can actually get it in closed form. So here is the q function. Remember that if h is complex 0, 1, then g, which is magnitude h squared, is exponential 1. So the PDF of g is just this one here, PDF of g. And so how can we solve an integral with the q function? The way to go here is to write down the q function in terms of its integral. So you take the q function and rewrite it in terms of its integral. Now the stuff we are integrating is non-negative, right? So basically here, the integrand is real valued and non-negative. And because it's real valued and non-negative, then we can apply Tonelli and reverse the order of integration. Okay, so here, if you look to this integral here, we should first do the integration with respect to v, and then with respect to g. And here is our integration region, right? Because g is from 0 to infinity, and v is from this thing here. I mean, that's the q function. The q function is the tail probability of a Gaussian standard Gaussian distribution. So you integrate from something to infinity, so over this region. Okay, so what is the problem with this integral? We don't know how to integrate e to the minus v squared, but we know how to integrate e to the minus g. So basically, because our integrand is basically non-negative, we can apply Tonelli and say, you know, we can actually do this integration in any order of our choice, and we want to integrate first with respect to g because it seems to be a manageable integral. Okay, so now we do an integration with respect to g, fixing v. So if you fix v, what is the range of v? So given v, g goes from 0 to the curve. And what is this curve? The curve is v is equal to the square root of 2 SNR g. And so basically square both sides. So v squared is equal to 2 SNR g squared. Sorry, g, because g is under the square root like this, g. And so g is v squared over on the curve. G is v squared over 2 SNR, right? So, so if you interchange the order of integration, now it's like you fix a v and you do the integration first with respect to g, and once you fix a g, once you fix v, g will go from 0, so that's the lower limit of g, and then till it hits the curve. This curve is, again, it comes from the definition of the q function. This curve here, the boundary here, is v is equal to the square root of 2 SNR g, and so this equivalently we can say that g is v squared over 2 SNR. And so now our integral, we will do first the integration with respect to g from 0 to v squared over 2 SNR, and then we will do the integration with respect to v from 0 to infinity. Standard double integral stuff that you have done a lot, like in a course in probability and so on. Okay, so now the integral is very manageable because integral of e to the minus g, basically from 0 to something, is 1 minus e to the minus, and then you replace g by this upper bound or upper limit of integration. Okay, and then we are left with this integral here. You may say that this integral, well, I mean, we get here v squared, but this is an easy integral because now the limits of integration are from 0 to infinity, right? So actually this integral can be written as two integrals. So this is one of them, and this is like integrating the standard Gaussian from 0 to infinity. So this is 1/2, right? If this is from minus infinity to infinity, it's like the Gaussian PDF, and the integral is 1. This is from 0 to infinity, so you get 1/2, and then you get another integral which looks like this. Okay, now what is this integral?
Yeah, I have a question. Why
Yes.
are we averaging over magnitude of h squared, not magnitude of h?
No, it's Lotus. You know. Okay, I mean, basically, you have a magnitude of h squared here, right? Right.
Yeah.
There is. I mean, Lotus. If you have a function of a let's not call it g. If you have a function of a random variable, the expectation of a function of a random variable, it can be done in a number of ways, right? It can be done in a number of ways. So one way is that you can take this thing, okay, multiply by the PDF of HDH. You can do this, okay? But here what we do is that we said, okay, magnitude h squared becomes g, and now we are basically solving with respect to g. Both ways are valid. Both
Yeah,
are
but
valid.
why with respect to g, not with respect to magnitude of h only? So I mean,
g is magnitude h squared. I don't understand.
yeah, is there any insight of averaging with respect to magnitude of h squared, not magnitude of h?
It makes the integral easier. You know, so yeah, I see now. So you want, like, say, okay, write it like this: q. Let's call the magnitude of h. You know, so magnitude of h squared. Let's put it like this. What you want to do is this: f of magnitude h squared, h, right?
Yeah, that's right.
You want to do it like this. It will give you the exact same result. But what is the PDF of the magnitude of h? Is Rayleigh.
Yeah.
Okay, which is different. So basically here we go for the magnitude of h squared, given that our function depends on magnitude of h squared.
Okay. Yeah.
Get what I mean? So our function itself, you know, so in what you are saying, there is no escape from what you are saying in some situations in which the q function ends up being the function of magnitude h only without squaring. Okay, but here we are sort of lucky, and basically under the q function, under the square root under the q function, basically it is magnitude h squared. What is magnitude h squared? Exponential. So the easiest thing is basically to think about your random variable, think about it as magnitude h squared, because it's the most convenient way. Can you do the problem with magnitude h? Yes. Can you do it with h itself? And you use basically the complex, you know, the distribution of the complex Gaussian? Yes. All those will give you the same result. But the most convenient one is simply to use the exponential, given that by the end of the day, the q function is, if it depends on the magnitude of h squared. Okay, and this will be like in the majority of cases. There is just, you know, one case we will talk about later in which you will hit the magnitude of h itself. Okay, so the last thing to say in this lecture is basically, what about this integral? How do you integrate something like this from minus infinity to infinity, e to the minus, let's say e to the minus eta x squared dx? One way of doing it, this is, you know, the way is like to say this is very close to be a Gaussian distribution. So basically, if I replace eta by 1 over 2 sigma squared, you know, this factor will be what you see in the Gaussian PDF. Given this, 1 over eta is equal to 2 sigma squared is 1 over 2 eta, so sigma is equal to 1 over square root 2 eta. This exponential, Okay, so it's like a Gaussian distribution without the normalizing factor. So what is this integral? You know, it should be, you know, if you integrate a Gaussian without the normalizing factor, you should get the factor, which is square root 2 pi sigma, right? So it will be square root 2 pi 1 over square root 2 eta. Okay, I call this thing matching with a PDF. So you get an integral and you don't know how to do it, but it looks like one PDF. So you just put it in the form of a PDF, okay, and enjoy basically that the PDF integrates. If you integrate it from minus infinity to infinity, it's 1. If you go from 0 to infinity, it's 1/2.